Welcome to a lesson on free undamped motion. In the previous lesson we learned if we have a mass attached to a spring as pictured here on the left, where m is the mass, k is the spring constant, c is the friction constant, big F of t is an external force, and x is the displacement, then the force of the mass is equal to mass times acceleration, or in our case, m times x double prime, where x double prime is the acceleration. The force of the spring is equal to negative k times x. The force of the spring is proportional to displacement, and it's negative because it's in the opposite direction of the force of the mass. And the friction force, given by big F sub f, is equal to negative c times x prime. Big S is proportional to velocity given by x prime, and again it's negative because it's in the opposite direction of the force. And again, if big F of t is some external force, we have the differential equation mx double prime equals big F of t minus cx prime minus kx. Or if we set the right side equal to big F of t, we have mx double prime plus cx prime plus kx equals big F of t. For free undamped motion, big F of t is identically 0, meaning it's always the zero function, and there is no friction force, and therefore c is equal to 0. So if c is equal to 0, and big F of t is equal to 0, the simplified free undamped motion differential equation is mx double prime plus kx equals 0. Sometimes the equation is given as x double prime plus omega squared x equals 0. To do this, we would divide both sides of the first equation by m, and then set k divided by m equal to omega squared. Let's take a look at free undamped motion in action. Here's an example of free undamped motion. Because there is no friction force or outside force acting on the mass, notice how the amplitude doesn't change, as well as the period. The displacement above and below the resting position remains the same as time passes. This is free undamped motion. Notice the free undamped motion differential equation is a second-order linear homogeneous ODE with constant coefficients, which we already know how to solve using a characteristic equation. The corresponding characteristic equation is mr squared plus k equals 0. Solving for r, we would subtract k on both sides, and then divide both sides by m, and finally take the square root of both sides of the equation, giving us r equals plus or minus the square root of k divided by m times I. Notice how we have two complex solutions, where if the solution is in the form of alpha plus or minus beta I, notice alpha is 0, and beta is equal to the square root of k divided by m. So looking at our previous notes below, we're looking at case 3 where we have two complex roots. Because alpha is equal to 0 and e to the 0 is equal to 1, notice the general solution can be simplified. It's often given in the form shown here above, where if r sub 1 and r sub 2 are two complex roots, then x of t is equal to a cosine omega t plus b sine omega t, where omega is the same as beta, equal to the square root of k divided by m. Using trig, this can also be expressed as c times cosine of the quantity omega t minus gamma. But when solving an initial value problem, it's usually easier to use a general solution that involves the sum. Let's take a look at an example. Suppose a 2 kilogram mass is attached to a spring with a spring constant of k equals 8 newtons per meter. The mass starts at 0.5 meters to the right of the resting position. The initial velocity is 1 meter per second. Determine the differential equation that models the motion, and then use the initial conditions to solve. So the given information is the mass is 2 kilograms, k is equal to 8 newtons per meter. The initial position, x sub 0, is equal to 0.5, because the mass starts at 0.5 meters to the right of the resting position. X is positive to the right of the resting position, x is negative to the left of the resting position. The initial velocity is 1 meter per second, giving us x prime of 0 equals 1. Because m is 2 and k is 8, we have the differential equation 2x double prime plus 8x equals 0. Let's first solve this like we already know how to do, using a characteristic equation. The corresponding characteristic equation is 2r squared plus 8 equals 0. Solving for r, we have r equals plus or minus 2i. So again, if the solutions are in the form of alpha plus or minus beta, alpha is 0 and beta is 2. So using the form that we already know, because alpha is 0 and beta is 2, we have the general solution not y of x, but x of t equals a cosine 2t plus b sine 2t, which we can also express as c times cosine of the quantity 2t minus gamma. Or again, if we use the definition using omega, just remember omega is the square root of k divided by m, which is the same as beta, giving us the same general solution. And now we'll use the general solution expressed as a sum to determine a and b using the initial conditions. So first, using x of 0 equals 0.5, we substitute 0 for t. Notice sine 0 is 0, just giving us a cosine 0 equals 0.5, and cosine 0 is equal to 1, giving us a equals 0.5. So now we know x of t equals 0.5 cosine 2t plus b sine 2t. The next step is to find the first derivative so that we can then use the initial condition x prime of 0 equals 1. X prime of t is equal to negative 0.5 sine 2t times 2 plus b cosine 2t times 2. And now we substitute 0 for t and set it equal to 1. But notice here we will have a sine 0, which is 0, so we'll leave that off, and we have b times cosine 0 times 2 equals 1. Again, cosine 0 is 1. Dividing both sides by 2, we have b equals 0.5. We now know the particular solution is x of t equals 0.5 cosine 2t plus 0.5 sine 2t. Before we go, let's take a look at this graph. Notice how the amplitude and period don't change because we have free undamped motion. At time 0, we can see the mass is 0.5 meters to the right of the resting position. I hope you found this helpful.